In the next few videos, we're going to talk about graphing polynomial functions. We're going to see several different types of polynomial functions, and sometimes it will be easy to graph these functions, and other times it'll be difficult. So to start off, we're going to look at a particular type of polynomial function, which actually helps us graph all other types of polynomial functions. So this type that we're going to look at is called a power function. So a power function is a monomial polynomial function. So it's a polynomial function that's a monomial. In other words, it only has one term. The function is going to look like this. F of x is equal to a sub n times x to the power n. There's not going to be any other terms. It's just going to be the leading term. The leading term is going to be the only term you see. For example, something like f of x is 9x to the fourth. This is a polynomial function. You can see the degree here is 4, but there's only one term. Another example would be something like 5x squared, and that's something we would know how to graph already. Okay, so for a polynomial function that's a power function, we're going to have some interesting pieces of information. If n is odd, so the degree is odd, then the shape of the graph, this is the overall shape, will look like x cubed. So it's either going to, let me draw this a little bit better. It's going to look like this, or it's going to look like this. So the graph of x cubed. The one that you choose depends on this leading coefficient. Let me put some space here. So let me do this. So here, what we're going to write here is that n is odd, then you're going to get one of these two shapes. How you choose is if an is greater than 0, what's going to happen is you're going to get this shape. And if an is less than 0, you're going to get this shape. And we're going to look at some examples, and we're going to prove this as well. That's the overall shape. Now, the higher the degree, if it's odd, the skinnier the graph will look. If your degree is even, then the shape of the graph will look like a parabola. So it's either going to be pointing up or pointing down. And how you determine this is if a sub n is greater than 0, you're going to be pointing up. And if a sub n is less than 0, you're going to be pointing down. So let me give you some examples here. So let's say f of x is equal to x squared. F of, let me call it a different function. We're going to do it in blue here. Let's say g of x is equal to x to the fourth. And let's do one more. Let's say h of x is x to the 10th. So you can see all of these numbers are even. So for each one of these, n is even. Okay, for x squared, we know what that looks like. It goes through the point 0, 0, because if you plug in 0, you get 0 squared, which is 0. We know it also goes through the point 1, 1. And if we plug in 2, we get 4. So the graph is going to look something like this. So this is f of x. Now the graph of g of x, let's do that in blue. Well, this graph also goes through 0, 0. Let's plug in another point. If I plug in 1, I'll get 1 to the 4th, which is 1. So it also goes through negative 1, 1 and 1, 1. If I plug in 2, though, 2 to the 4th is actually 16, which is going to be way up here somewhere. So I'm just going to say, let's say this is 16. And if I plug in negative 2 to the 4th is also 16. So you're going to have a point way up here as well. So what's going to happen is you're going to get a graph that's very similar. It's a little bit thinner than the parabola, the original parabola. So it's going to look something like this. So it's like F, excuse me, and actually at the bottom part of this G actually goes a little bit lower here. And then if you have h of x, what will happen is you'll go through these 3 points again, but if you plug in 2, you get 2 to the 10th, which is a really large number. So we're going to be way up here somewhere. So if we try to draw this graph, it's going to be a little bit skinnier than the blue graph. But the idea is it's going to look generally the same as the rest of them. So I'm just going to do this I'm not going to go all the way up there. I'm just trying to sketch this graph so you have an idea of what it looks like. So it's going to look similar to the other ones, but just a little bit closer to the y-axis. So it's going to look something like this. Maybe if I draw it over here. So here's one of them. The other one's going to look a little bit more like this, and then the red graph is a little bit thinner. Something like that. So whenever you have an even number, if you make this 100 or 250 or 3054, as long as it's even, then you're going to have a graph that looks like a parabola. It's just going to be stretched. So the idea here is it's going to be going up like this. Now what happens if I multiply by a constant for each one of these graphs? So I put a 3 here. Well, it just makes the graph skinnier. So it will make each one of these graphs a little bit skinnier, but it'll still be a parabola pointing upwards. But if I multiplied by a negative, what happens? Well, this would be a reflection. So all of these graphs will now be pointing in the opposite direction. I wonder if I could rotate this. Well, I don't think so. So like if I put a negative in front of each one of these graphs, so I put a negative x squared here, what's going to happen? I'm just going to sketch this graph. It's not going to be perfect, but it's going to look something like this. This would be the green graph. And if I put a negative in front of the x to the 4th, well, it just flips, just like transformations of functions, it flips this graph. So it's going to look similar. So it's still going to be skinnier than the green graph, and it's going to be pointing downward, so it's still a parabola. And for the last graph, again, it's going to be skinny, but a little bit skinnier than the other two, like that. So a negative in the front flips the graph upside down. So when you have a negative, you're going to have something that looks like a parabola pointing downward. And that's what I wrote here. So if n is even, then the shape of the graph is a parabola. And if the leading coefficient is greater than 0, so you have a positive, you're going to be pointing upwards. And if the leading coefficient is less than 0, you're going to be pointing downwards. Now let's talk about this shape here. So let's change this green, blue, and red graph. I'm going to give you a function we know already, which is x cubed. And let's choose some other ones, like x to the 5th and x to the 7th. Okay, if we have x cubed, of course you can plot a few points to give you the idea of this graph, but this was one of the graphs we learned, we memorized as a parent function, You can see if I plug in 1, I get 1. So I have a point at 1, 1. If I plug in -1, I get -1. And you can plug in more points, like 2 cubed is 8, and so on. But the overall shape of this graph looks something like that. Which, of course, if you zoom out or change the perspective of the axes, so maybe you put like less numbers here and more numbers here or something, the idea is the shape looks something like this. You can see that you're going down, and then around here you kind of change a direction in a way. You kind of start straightening out, and then you start going back up. So it kind of looks like this. And if you graph x to the 5th, let's do that one in blue. Oops. Well, similar thing's going to happen. You're going to go through these same points, but if you put 2 to the 5th here, before you got to the 2 cubed, which was 8, but 2 to the 5th, I think that's 32, which is going to be even further up. So what's going to happen is this is actually going to kind of come out a little bit. But it's going to be like this original green graph, but stretched out. And then if you graph something like x to the 7th, well, then you'd have 2 to the 7th, which would be really a big number, but you'd still have these 3 points here. So this one would go even further, like towards this y-axis. It's going to look very similar to the other ones, but a little bit skinnier. So let me draw them here, just have an idea here. So they're all going to look similar. They're all going to look like x cubed. They're just going to look like x cubed kind of stretched out. So when you have an odd degree, as long as this odd degree is 3 or bigger, what's going to happen is you're going to look like the x cubed graph. Now, if you put a number in the front of these, if it's positive, it just stretches these graphs even more. However, if you make it a negative, so if you put a negative x cubed here, and a negative x to the 5th, and a negative x to the 7th, well, remember about transformations of functions, if we put a negative on the outside, it flips the graph upside down. So what's going to happen is for this green graph, you're going to have these 3 points, but it's going to look more like, I'm just sketching this, it's not perfect, but like this. It's going to be the same graph but flipped upside down, and so will these. These will look very similar, but a little bit skinnier. So something like that. So the idea here is, whenever you have an odd degree that's 3 or bigger, then you're going to look like x cubed. And that's what we wrote up here. If n is odd, then the shape of the graph is like x cubed. If a sub n is greater than 0, it's going to look like the normal x cubed. And if it's less than 0, it's going to look like x cubed flipped upside down. I also want to say that for each one of these cases, n is going to be greater than or equal to 3. And then for this one, n is greater than or equal to 2. So the degree of your polynomial function has to be greater than or equal to 2 for an even graph, and greater than or equal to 3 for an odd graph. And that's because if n is 1, we know that we just have a line. And if n is 0, which would make it even, we would just have a line as well. And so it doesn't look like a parabola. It's only when our degree is bigger than 2, we have something that's a parabola and even. If the degree is odd and bigger than 3, then we have something that looks like x cubed. So the reason we're learning about this is now we already see how to graph monomial polynomial functions. So now we can just graph anything. Let me give you an example. We can graph anything that's a monomial. So let me just give you a random example. Let's say f of x is equal to 15x to the 20th. Well, this has an even power, is even degree, and the coefficient 15 is greater than 0. So this graph is going to look something like this. It's going to be parabola shaped. It's going to go through 0, 0. But then we can just plug in a couple of points. If we plug in 1 here, we get 1 to the 20th times 15. So we're going to have 15 way up here for when we plug in 1. So here's 1 here. So 15 is way up here. So you're going to have a parabola-shaped graph that like goes through 15. So it's going to be really stretched out. Oops. So something like that. That's how you would graph this. You know it's parabola shape, so you just need to put a point at 0, 0, because that's an obvious point. And then you can put a point over here, which would be, you could do 115. Of course, you could do something else, and then you could get the other point. And if I put a negative in the front of this, let's say I made this a negative 15x to the 20th. Well, because then negative 15 is less than 0, your graph would be pointing downward. So it would look something like this. If I gave you the polynomial function, let's say, let's do it in blue, g of x is equal to 2x to the 75. Well, you notice that this number is odd and is greater than or equal to 3. So this is going to look like this because 2 is greater than 0. Our two options when it's odd is to look like this one or to look like this one. And the way we choose is to see if this number in the front is greater than 0. If it's greater than 0, we go with this one. And so we have an idea of what the graph looks like, and we just need to plot a few points. Obviously, it goes through 0, 0. If you plug in 0, you get 0. And then you can plug in 1 here. You get 1 to the 75th, which is 1 times 2. So it would go through 1, 2. And then if you plug in negative 1, you'll get a negative 2. So this graph is going to look something like this. Okay, great. So we have a good idea of how to draw a monomial that's a polynomial function. And power functions actually will help us draw more complicated polynomial functions. So we're going to keep that in mind for later. Okay, so the overall objective is to graph some polynomial functions. We're going to break this into 3 pieces here. The first piece is we're going to learn how to graph polynomials by using transformations. This will be the easiest type of polynomial to graph. This will be stuff that we've seen before and how we've learned to move those parent functions around. You just have to be able to identify that this is the type of function that you can actually use transformations for. So that's the first thing we're going to learn how to graph. Then after we learn that, we're going to learn how to graph polynomials that are factored. The factored form of a polynomial is a little harder to graph than using transformations, but we can graph it, and we just have to be careful. We have to graph using roots and things like that. So that's the next type of function we'll learn how to graph, polynomial functions that I've already factored for you. Then the final step is we're going to learn how to graph polynomial functions that are not factored. So let me give you an example of each one of these so you have an idea of what I'm talking about. So for this first step, the type of functions we'll learn how to graph is something like this: 3x to the 7th plus 10. Here we can use transformations of functions because we have x to the 7th. This 3x to the 7th here is a power function. So we can either think about just working with x to the 7th or 3x to the 7th, and then we have a plus 10 on the outside, which just means we shift the graph up 10. We'll see things like that. Or we'll have something like, let's say, negative 2x plus 5 to the 8th minus 4. This is another function that's set up for transformations because we have the power 8, which tells us that we're going to look like a parabola. This negative 2 in the front tells us the parabola is pointing downward. And then because we have this plus 5 in, we shift to the left 5, and then we shift down 4. So this is everything we've seen before. For the second step, you're going to have functions that look like y is equal to 3, x minus 2, x plus 4 to the 4th. And then I can even throw something else in, x plus 1 cubed. So you're going to have a polynomial function, but it's factored. I've got all of these pieces here. And what we're going to do is we're going to set it equal to 0, and we're going to be able to find the roots. And then finding the roots will help us graph such things. So once we learn how to graph this kind of stuff, then we'll learn how to graph polynomials that are not factors. So something like x cubed minus 4x squared plus x minus 1. Or something even more complicated like 15x to the 10th minus 4x plus 12. So these are not in the factored form, but we will be able to use things that we've learned in the first two steps to factor them and to get them into this form where we can graph them more easily. So this is going to be the least complicated way to graph functions, but it has to look a certain way for us to use this step 1. Then we're going to go to step 2, which will take a little more time to graph, and then step 3 will be the hardest to graph. So let's start with step 1. Let's graph the following polynomial functions. Here I have f of x is equal to 1 plus x plus 2 to the 5th. Okay, so we're going to start off. Make sure you put some space on your paper to draw something here. We're going to try to find a parent function. And the parent function I'm going to go with is y is equal to, in fact, let me label it something else. Let's say f1 of x is equal x to the 5th. Because this looks like x to the 5th, right? This is x to the 5th, but then I plug in a 2 inside the x and then a 1 on the outside. Now, we learned that this is a power function. The degree here, n is 5, which is odd. So the graph is either going to look like this or it's going to look like this. And because the leading coefficient is 1 for this power function, which is greater than 0, we're going with this x cubed looking graph. So let's try to sketch the graph of x to the 5th. Let's go, I'm going to do it in green. So x to the 5th goes through 0, 0. Plug in 1, you get 1. Plug in -1, you get -1. And just sketch the graph of something that looks like x cubed. Remember, this is a sketch. It's not perfect. If you want to get a better sketch, plug in 2. 2 to the 5th would be 32. So you'd have something way up here. So you can see that my graph looks like it's going through 2 to the, maybe 2 to the 5.5. 2, when I plug in 2, I get 5.5, which is not correct, but I'm just sketching. I'm just trying to get an idea of what this graph looks like. Okay, so now I have my parent function. The next thing I want to do is I want to shift this graph around by looking at what I have here. So I'm going to define a new function. Let's put it in blue. f2 of x. What I'm going to do is I'm going to take the original function f1x and I'm going to plug in plus 2 into that function, which will give me x plus 2 to the 5th. So when we plug in a plus 2, that means we shift to the left 2 units. So 1, 2. This 0, 0 now goes to negative 2, 0. So the graph is going to look something like that. Erase this graph now. So now we have the graph of f2. Now to get to this final stage, we define the new function, which is f of x, if you want to do that. F of x is equal to taking this function f2, and what do we have to do? We have to put a plus 1 on the outside. That will give us what we want, which is the graph that we wanted to graph. So we just shift everything up 1 unit. So you can see this is very similar to what we've done. We just have to know the parent function to begin with. So here is a sketch. Let me do a better job here. The sketch of the function we want, f. Okay, let's try another one. Here I have g of x is negative x to the 6 plus 1. Okay, identify the parent function. The parent function should be f of, let's say f1 of x is equal to x to the 6th. We could also say negative x to the 6th if you want to do that. It doesn't matter. That's what I'm going to do. I'm going to say negative x to the 6th right here. This is a power function. We see that x to the 6th, we have an even degree, which means we're either pointing up as a parabola or pointing down as a parabola. Because we have this negative, we're going to point downwards. Okay, let's just graph some points for this parent function. So if I plug in 0, I get 0. If I plug in 1, I get negative 1. And if I plug in negative 1, I also get negative 1. So the graph is going to look something like this, sort of like a parabola. Now, if you had chosen to go with the original function, just x to the 6, without this negative, then the negative will, when you graph it, you'll flip it upside down with transformations of functions. So it doesn't matter how you start here. Well, to go from here to what we want, g of x is equal to taking this function f1 of x and adding 1 to the outside, which just means we shift this graph up by 1 unit. So let's put this one in black and then draw like this. And then erase this parent function. So the graph of g looks something like that. It's probably a little bit skinnier, but that's the overall shape. Let me see what else I have here. Okay, I've got one more that I want to do. I'm not spending a whole lot of time on this because we've done transformations of graphs before. So here I have negative x minus 3 to the 100. Start off by trying to figure out what your parent function is. The parent function, I would say, is x to the 100. So you could say f of x is equal to this, and you could also go with negative x to the 100. Okay, so this is even, which means it's pointing upwards. Also, because we have the leading coefficient is positive, it's a parabola looking. So let's draw some points. Of course, it's going to be much skinnier than that, but that's the idea of what it looks like. Then to get to this stage, well, we can define a new function, f1 of x. We can say that it's f of x with minus 3 plugged in, x minus 3, which would give us x minus 3 to the 100. And that means we shift the graph over 3 units. So 1, 2, 3. It's going to look like this. And then the next step is that h of x is f1 of x, but with a negative on the outside. And when you have a negative on the outside, you flip with respect to the x-axis. And you can plug in points to double check this, because if you plug in 3, so what you're going to get is negative x minus 3 to the 100. You can see when you plug in 3, you get 0, 0. Sorry, when you plug in 3, you get 0, so you get the point 3, 0. When you plug in 4, you're going to get negative 1. And when you plug in 2, you're going to get negative 1. So the graph is going to look like this. And this is the sketch of this graph right here. Okay, so let's move on. I think we have a good understanding of how to graph polynomial functions using transformations. Now we're going to talk about polynomial functions that are in a factored form. So we're going to have to look at several pieces of information before we can actually graph it. One thing we need to talk about is the zeros of a polynomial function. Okay, here I have sketched for you a picture of a polynomial function. So this is a polynomial function. Abbreviate it. And notice that it has roots which, remember, roots mean where it intersects the x-axis. It has the root of x is equal to negative 5 and x is equal to 2, because I go through negative 5 here and 2 here. Something else I can tell by looking at this graph is at negative 5, we intersect the x-axis. In other words, I go straight through the x-axis there. But at x is equal to 2, I just touch and go. So I don't go through the x-axis, I just touch it and then I go back. So I touch the x-axis at this root. Well, what's interesting is when you have a polynomial function and you factored it, and you've got it in this nice factored form, you can tell when you're going to touch the x-axis and when you actually cross it by looking at the multiplicities of the roots. So this function here, f of x, when you factor it, you're going to have x plus 5 raised to an odd power and x minus 2 raised to an even power. When you have, so let me give you an example of what this function could look like. F of x is equal to x plus 5 cubed times x minus 2 squared. I'm not saying that this is the exact formula for this function, but the graph of this function is going to look almost identical to it. The hump here might not be as big, or it might be even bigger, but the idea, the graph is going to look virtually the same. Because whenever you have an odd number here, you intersect through that point. And whenever you have an even number here, you just touch it and go. And why I knew to put the opposite, notice that I have x plus 5 instead of x minus 5 and x minus 2, is because remember how we find roots. We set this function equal to 0, and then we set each piece equal to 0. And then you take the cubic root and the square root here, and you get x plus 5 is 0, x minus 2 is 0, so you get x is 2 and x is equal to negative 5. So in the factored form of this function, I would have, whenever I have a root of something, I take the opposite on the inside. And this could also be x plus 5 to the 9th times x minus 2 to the 4th, or just x plus 5 to the 1st power and x minus 2 to the 20th power. What we know is when we go through those roots, whatever the multiplicity here is, multiplicity is the degree of this factor, the highest degree of the factor that you can find. If it's odd, you go straight through, and if it's even, you just touch. And I'm going to write this down a little more. I'm just trying to explain it right now. but I'll put it in a summary a little bit later. I want to show you another example. So here I have some kind of polynomial function. Notice that this side goes down and this side goes down. Notice that I have 1, 2, 3, 4, 5 roots. Let's write this down. This function has 5 roots. What are the roots? So x is equal to, this looks like -6.5. Because here's -6. 2 of these is equal to 1 unit difference, and it goes through this one. Then we have x is equal to -3. Then x is equal to 0. Let me move this down a little bit. X is equal to 3, and x is equal to 7. Let's figure out if we touch and go at any of these roots, or if we just go intersect the x-axis at these roots. So at -6.5, I intersect the x-axis. In fact, I'll copy this because we're going to intersect a lot. Here I touch and go. Here I intersect. Here I intersect. And here I intersect. It's only at -3 that I touch the x-axis, but I don't intersect. So what's going to happen is when we see the function, the actual written function of this, we're going to have something that looks like a number on the outside. So you could have something like, I'm just going to put a for a number, x plus 6.5 to an odd power times x plus 3 to an even power. Then you're going to have an x minus 0 to an odd power, an x minus 3 to an odd power, and an x minus 7 to an odd power. So an example of a function that would look similar to this, it might not have the same exact heights for these humps, but it would look almost identical to it, would be -3 x plus 6.5 times x plus 3 squared times x minus 3 cubed times x minus 7. Because look, this has an odd power, this has an odd power, this one has an odd power, this one has an even power, and I think I said this one has an odd power. And this number in the front, I chose -3, and there's a reason I did that, because this graph is pointing downwards. That has to do with the power function, and I'll describe that a little bit later as well. But the number in the front has to be negative for it to be pointing downwards, because overall this graph looks like this, which is similar to the parabola. It looks like a parabola, but with something strange happening in the middle. And that tells me that I have a function that's leading term, the degree of the function is going to be even, and the leading term is negative. And we'll look at that later as well. Okay, so one example of something we've seen already is a parabola. And I think me going over this should really help you understand things like touching and going and stuff like that. So let me give you a graph of a function we know how to graph, which is something like x plus 5 squared. And let's do one in green as well. Let's just do the original x squared, okay? To graph this x squared, what do? We go through 0, 0. This is the parent function we know and love, x squared. So this is the graph of g. And this function here is the graph of g moved to the left 5 units. So let's move it here. So this is the graph of f. What do you notice about the x-intercepts here, or the roots of the function? For the function g, we go through 0, 0. Notice that this is in factored form. This is the same thing as g of x is equal to x minus 0 squared. And this number here, which is the multiplicity, is even. And we touch this. We just touch and go. And then for the blue function, you can see that the root is -5. When we set this equal to 0 and solve for x, we take the square root of 0, we get 0, and you can move the 5 over. So you see you get -5. And this number here is even, so we touch and go. Now let's look at a function of a parabola that doesn't touch and go. Let's say we have something like f of x is equal to x squared minus 1. How would we graph this? Well, this is the parent function x squared shifted down 1 unit. So it would go right through here, here, and here. And you can see I intersect the x-axis here. But what is the factored form of this function? This is x minus 1 times x plus 1. And you can see the powers on both of these factors is 1, which is an odd number. And because it's odd, you can see we intersect the graph at the intercepts. We go right through the graph of the x-axis. Okay, so let's write a little summary on zeros, multiplicities, and graphs. Okay, so when you have a function, let's say you have a function f of x is equal to a x minus k1 to some power r1, x minus k2 to some r2, x minus kn to some rn, where k1, k2, all the way to kn are distinct roots. R1 is the multiplicity of the root k1, and R2 is the multiplicity of the root k2, and so on. Rn is the multiplicity of root kn. If Ri, so this could be any of the R's. If any, maybe, because I'm not sure if you're good with this kind of notation. This is a common notation in mathematics, but like, let me write it this way. If any R, any of the R's is odd, then we touch and we intersect the x-axis. Yeah, let me do it like this. Intersect x-axis. If any R is even, we touch the x-axis, but we don't intersect. And let me give you an example so you can see this visually, because I know sometimes, especially people who are new to mathematics or this, when they see all these letters, they get a little confused. So I always think it's a good idea to look at an example. So make sure you write this stuff down. You can go back and watch the video a few seconds ago. But let me write down an example of this function. So let's say f of x is equal to 10, x minus 3 squared, x plus 4 to the 5th, x minus 8, just like that. So this is in that form above. Let me scroll out a little bit. So I've got a number in the front. It could just be 1. You don't even have to put anything there. But I have x minus something. And then here I have x plus, which is the same thing as minus and -4. And then I have x minus 8. And you can see that here I have 3 roots. So in this particular example is 3, just because I have 3 roots. And then I have 3 multiplicities. This number is the multiplicity of this root. And this number is the multiplicity of -4, and the number 1 is the multiplicity of 8. So you can see that 3, -4, and 8 are roots, and 2 is the multiplicity of 3. 5 is the multiplicity, I'm going to abbreviate this, of -4. And 8 is the multiplicity of, 1 is the multiplicity of 8. And what that tells me is this number is even, so we're going to touch the x-axis here. This number, 5, is odd, so we're going to intersect the x-axis. And this number is odd, which tells me I'm going to intersect the x-axis.